Is it visible?
Yes, yes, it is visible.
Uh, so this was your previous experience are already explained. So 1 minute. You can take IRF 1010N. ठीक है? IRF 1010M. It is available in Multisim. Whatever the values given in manuals, that manual value I have given. Okay. Then this is your pulse voltage setting. Pulse voltage setting. You have to. Okay. 1 minute. एक मिनट. Experiment number 8 na. This one.
Yes.
So here written pulse voltage that is 5 e to the power minus 6 second टाइम पीरियड 2 e to the power minus 5. अच्छा यहाँ पे तुमको ये जगह पे चेंज करना है. इसका जो बाय डिफॉल्ट वैल्यू है. 1 मिनट थोड़ा मैं अभी इसको और एक बार ले जाता हूँ. किया था लास्ट टाइम में इसको किया था. सिग्नल वोल्टेज जनरेटर पल्स वोल्टेज. ठीक है. इसका जो बाय डिफॉल्ट वैल्यू है ये तुम्हारा 0 वोल्ट था. ये 6 वोल्ट्स. ठीक है. पल्स विड्थ जो दिया है यहाँ पे चेंज करना है पल्स विड्थ एंड पीरियड में. ये होगा 5 e to the power minus 6. पीरियड होगा तुम्हारा 2 e to the power minus 5. 5 e to the power minus 6 2 e to the power minus 5. Okay. Now एक मिनट और एक बार ऑन करते हैं. दिस इज योर चैनल बी. ठीक है. और ये भी जो स्ट्रेट आ रहा है ये भी स्ट्रेट नहीं, इसको भी जूम करने से आएगा। हॉरिजेंटल जूम करना, वर्टिकल जूम करना पड़ेगा ना। निश्चित जो चैनल है, ठीक है। चैनल बी का मैग्निफिकेशन ज्यादा है, चैनल ए का ये है, चैनल बी का जो मैं बोला था, तुम भी इसको कर सकते हो। तो यहाँ पे तुमको चेंज करना पड़ेगा ये जो पल्स विड्थ थे एंड टाइम पीरियड में, ठीक है। और यहाँ पे तुम सिमुलेशन एनालिसिस में भी कर सकते हो, सिमुलेट एनालिसिस, ट्रांजिएंट एनालिसिस 0.01 0 पॉइंट, देखते हैं 1 सेकेंड में आउटपुट IL1 करंट थ्रू दिस इंडक्टर एंड V4, ठीक है। और तो टाइम का जो दिया था ठीक दिया था, टाइम का 0.01 में भी कर सकते हो, 1 मिनट। सिमुलेट एनालिसिस ये 0.01 में करोगे, हाँ ठीक, ठीक है। बस ये तुम्हारा V4 मीन्स वोल्टेज, वोल्टेज across the load and IL means current through inductor। तो इसको मैग्नीफाई कर सकते हो, सेकंड वाला जो करंट वाला वोल्टेज को मैं ऑनसिलेट कर देता हूँ। ये तुम्हारा करंट है, जैसे आ रहा था ग्राफर में भी आ रहा है और एनालिसिस में भी आ रहा है, ठीक है।
यस सर।
ओके, तो जो भी देखो यहाँ पे तुम्हारा सब कंपोनेंट सेम है, सिर्फ ये वाला तुम जो स्विचिंग डिवाइस मॉसफेट IRF है 1010N, इसको लेके करो, ये मल्टीसिम में अवेलेबल है, ठीक है। यहाँ पे जाओगे मॉसफेट आई, यहाँ पे लिख दोगे 1010N, IRF देखो फर्स्ट वन, IRF 1010N, दिस वन, ठीक है। तो इसी हिसाब से करना पड़ेगा सबका, वेवफॉर्म ठीक आएगा, अगर ठीक से तुम करोगे तो आएगा। सार का जो मैनुअल है बहुत स्टैंडर्ड है वहाँ पे, तो उसमें वेवफॉर्म्स आएगा ही आएगा, 1% प्रॉब्लम नहीं है। ओके सर, मैं स्टूडेंट्स का ले जाऊंगा, थोड़ा
Sure,
अटेंडेंस।
sir. Attendance really. Yes, yes.
ठीक है, ठीक है। सो 1 मिनट, अटेंडेंस ले जाता हूँ, डाउनलोड्स, अटेंडेंस वेडनेसडे। ओके, रोल नंबर 132
Present sir.
337
Present sir.
338 338 338 340
Yes, sir.
341 341 342 342।
हेलो।
हाँ
यस सर।
थ्री, हाँ कौन सा रोल नंबर? 341।
342, sir.
ठीक है, 342। 343।
Yes, sir.
345।
Yes, sir.
347। 347। 349। 349। 351। 351। 352।
Present, sir.
353।
Yes, sir.
354।
Present, sir.
355। 355। 356।
Present, sir.
357। 357। 358।
Yes, sir.
358। 359।
Yes, sir.
361।
Yes, sir.
362।
Yes, sir.
363।
Yes, sir.
364।
Yes, sir.
365।
Present, sir.
366।
Present, sir.
367.
Yes, sir.
368.
Present, sir.
370.
Yes, sir.
371.
Yes, sir.
373. 373.
Sir, he wrote in the message book. His mic is not working.
Okay. 374.
Yes, sir.
375.
Yes, sir.
376.
Yes, sir.
377.
Yes, sir.
378.
Present, sir.
379.
Yes, sir.
380.
Present, sir.
381.
Yes, sir.
382. 382. 383.
Yes, sir.
384.
Hello.
Yes, sir.
Sir, 382 present.
384.
Yes, sir.
Sir,
Sir, 384.
382.
380.
Hello?
अच्छा, 382 present.
Yes, sir,
Hello?
382 is
Sir,
present.
sir, 349%.
349 present. अच्छा,
Hello? Yes, sir.
385. 385. 385. 385। हाँ, कोई प्रेजेंट है इस देखो 338, 341,
Sir,
347।
Sir, 33 present.
कितना?
338.
338। ठीक है। 341, 347, 351, 355, 357,
Sir,
358,
357.
385।
Sir,
Three five
357.
one. Present, sir.
एक बस
sir,
सिंगल बोलो, इंडिविजुअली बोलो।
sir, some of them have written in the chat box. The mic is not working.
Sir,
नहीं, जो
357.
जो लिखा है मैं उसका भी मार्क किया हूँ। एक मिनट देख लेता हूँ। 385। 385 प्रेजेंट।
Sir, 357.
ठीक है। 35 से 351। ठीक है। 351।
357.
Sir, present.
357 कौन है? 357। और लास्ट में कोई बोला? ठीक है, एब्सेंट सर, एब्सेंट स्टूडेंट्स नेम बोल देता हूँ। 341 347 355 358। ठीक है, ओके। 341 347 355 358, 4 स्टूडेंट एब्सेंट है। ओके, ठीक। ठीक है सर, हो गया।
ओके, ठीक ठीक।
347।
Just for a moment. Is my document is visible from your side?
Yes, sir.
Okay. Yes. So last class we have discussed about different DC-DC converter, different topologies of DC-DC converter. That was very simple simulation. Okay. So today I am going to discuss about the same thing but in closed loop manner. Okay. So what happened? You are in 8th semester. I think you know the basic motivations of the why we are going for controlling the closed loop operations. What is the significance of open loop operations? Okay, means we can think we should not think like that. There is no meaning of open loop study. Basically, we did it for we are normally focused on the open loop study to find out that means system identifications, means where it will be started, then at how much value we can go for their saturation level. Okay, means if you have some system, so initially we have started in power electronics point of view. I'm telling you, if you have one system, means you can have any DC-DC converter. Now you are controlling your DC-DC converter, means try to study the performance of the DC-DC converter in open loop. So you have started with duty cycle at 0.1. Okay, means you can say like a 0.1 is difficult, so you can say like that duty cycle with 1. Then gradually you can increase 1% up to 100%. Now you can see what has been changed, what kinds of change is observed in the output. Okay. So by that way you can understand what is the performance. Okay, what kinds of performance you can see of your system dynamics, means of your converter dynamics. Okay, in control terminology it is called system identifications. Okay, so there are other methods also available in control. So designing of the any of the classical control designing, like you say like that PI control, PID control, lead control, lag control, lead lag control, lag lead control. Okay, but in case of DC-DC converter, those converter means specially having means specially buck boost converter, buck boost converter, and some derived converter based on boost and buck boost having non-minimum phase problem. What do you mean by the non-minimum phase problem? That's a very simple concept from the control system. So it having one RHP 0, means right half plane 0 in their plant transfer function, means in their control to output transfer function. Okay, so derivation of the transfer function also very important. Basically we can say like that all those DC-DC converter is working in linear mode, but they are working in the switched mode. Okay, that's the difference between the linear power supply and switch mode power supply. Okay, in linear power supply the operating zone is that is called quasi it is known as the quasi what is the term? Sorry, quasi linearized zone means, you know that if you see the characteristics, there is some, initially it is some cutoff region, there are some linear mode of operation. Okay, then it will be saturated condition. Okay, that linear mode of operation, that is known as quasi linear mode of operation. Okay, so you have to choose that value when you are controlling your converter in the linear mode of operation, means linear power supply. Okay, but here you are using the converter as a switch mode. Switch mode means either it will be means cut off region, or it will be in saturated region. So what kinds of non-linearities you can observe in case of buck converter, boost converter, of any other DC-DC converter, that is called switching non-linearities. Okay, so we have to convert that kinds of system, means it's an example of a nonlinear system. Now we should convert that system to our linear models by using LTI system, means linear time invariant system, means you can use the transfer functionized model. So some methods are there. First you have to write the state space equations on it. Okay, then after writing the equations, you have to use some linearizing method. Okay, what are the linearizing method? First state equations for on condition, means when switch is on. Then you have to write the state equation, means state space equations for which when switch is off. Then what happen, you will get some duty weighted. Okay, duty weighted state equations, means that d value may be 0, may be 1. Okay, then you have average both of them. In my last class I told you na, for DC-DC converter, means 4-quadrant chopper, that I was discussed. Okay, the 4-quadrant chopper, so you have to see the output voltage. Okay, by average output voltage by variation of the duty. Okay, so means on time means V out into D on, sorry, V out into T suffix on, plus V out into T off, means off time voltage, whole divided by T on plus T off. So you are getting some average value. Okay, duty weighted average value, that is your output voltage. Okay, same kinds of thing also happened here. Okay, so duty weighted response we will get. Okay, then you have to use some perturbation method. Okay, for making it linearized. Okay, so then you are using perturbations. After doing the perturbation, then you have to separate the DC component. Okay, and the AC component. The DC component stands for your steady state value. Okay, and AC component stands for your transient value. Okay, so then what happened, that DC component it's a steady state value. Okay, that is okay, but AC component is more important for finding out the dynamics of your system. Then AC component, how do you get the transfer function? Then both sides you should use the Laplace transformation. Okay, after doing the Laplace transformation, you can get the different types of transfer function. Okay, one of the important transfer function is control to output transfer function, that is known as the Planck transfer function. So sometimes what happen, not for the buck converter, for boost, buck boost, and derived converters from buck and derived converter from boost and buck boost converter, you will get
Hello, sir.
some. Yes. Hello.
Sir, I'm Abhilipsha 347. Sir, I was disconnected for 15 minutes, so I didn't respond to the attendance.
Next, actually, that attendance was taken by Ramaprasad sir. Next class, you please talk to him. Okay.
Okay, sir.
Okay, that attendance register is with him actually. Okay. Take. Let me finish, then we can talk. So then what happened? Then you are getting the transfer function. So some converter that I am telling you, boost, buck boost, having, if you see the Planck transfer function on 0, RHP 0 you can observe. So what will be the problem of that RHP 0? Means minus component is there. Okay, in above, means in your numerator. So what happen if it is x, means s minus something, then what happen? Then it will provide you that additional 90-degree phase lagging. Okay, if it's a second order system, so already 90-degree plus 90-degree, 180-degree phase lagging is there. Then again one RHP is 0, so another minus 90-degree, another 90-degree phase lagging. So minus 180-degree phase lagging, minus 270-degree phase lagging you can observe. Okay, so that's why it is known as non-minimum phase. Means it's a maximum phase lagging system. Okay, so by that way, some of the cases you cannot use that such conventional controller. Classical controller you may use, but these kinds of direct controller you cannot be used. So some PI plus we are using lead, PI plus lead controller or PI plus lead controller. Sometimes we are also used. Why we are using lead controller? For boosting of the phase. Okay, lead controller having inherent capability to boosting of the phase level. Okay, so that's the option. So you can get it from first open loop system, then try to understand the system dynamics. Then you know the different methodology you can use like ZN method, set point method. Okay, then reference stacking method for designing of any of the classical, especially for PID controller. Okay, then one by one you can go for the closed loop control systems. Okay, so here we are using only very simple controller, that is PI controller, proportional integral controller. So you can use exact that I am using that parameter. If you do not, if you are not able to use that exact parameter value, then what happen, your response will not coming appropriately. Means whatever the results I am getting here. Okay, so I am using all those design value. Okay, here I am taking, it's a buck converter. Here I am using one voltage, that is 10 volt receive supply is there. Then one MOSFET I am using that IRF 450. Okay, one mood diode is used, mood 160. Then current probe is there, 1 millivolt per milliampere. Then what is 1 ohm? That is the ESR, means equivalent series resistance of inductor. Okay, your inductor values is 13 millihenry. So equivalent series resistance. Okay, that is your equivalent series resistance of the inductor. So that you can say like that, impurities of the inductor or parasitic elements. Okay, that inductors, that additional resistance, that is RL. Okay, ESR inductor and ESR capacitor. Here you can see it is R2 is your, R1 is your ESR of inductor, equivalent series resistance of the inductor. Ideally it should be 0, but practical cases it is present. Okay, the same thing also happened with the capacitor. It's a standard capacitor, so it having some inherent parasitic values. Okay, so that is 10 millihenry. How to get those value? That R2 and R1 value. R1 value may be calculated by using, if you have the inductor, so you can calculate it. Okay, so how much series resistance is there? Okay, so it's possible. Okay, calculations of the resistance. But in case of capacitor, you have to download the data sheet of that capacitor and you have to write that one. So standard capacitor, whatever you, if you are using 100 microfarad, so how to get those value? You have to data sheet, you have to download the data sheet of the 100 microfarad capacitor. Then from the data sheet you should write the value, ESR value. Okay, arbitrarily should not be written anything. So it's a design problem and it is working in the closed loop, so you have to be very careful. Then what happened here, you can see that we are using load resistance of 20 ohm. Then we are using voltage divider circuit. Why voltage divider circuit? Basically the control signal should be below 15 volt. Okay, basically you know that positive, negative and positive voltage I am taking here 15 volt, 15 volt. Okay, means these are the biasing voltage of that operational amplifier. Here you know that LM311M we are using as an operational amplifier and one TL084. Okay, both of the operational amplifier using, it's a comparator, it's an op-amp. So but they are in op-amp. Okay, differential operational amplifier, it is comparative. Okay, so we are using that value, so stepping down that value means sensing that voltage level. Okay, so 5 volt I am giving as a reference. So if you are getting how much, it's a buck converter, so how much voltage you are, how much voltage is arise here, so it will be stepping down up to, scaling down up to 5 volt. Okay, that I am taking. So after that we are using PI controller, so capacitor series with some RC value is there. Okay, that is your PI controller. Okay, and we are also comparing the error. Okay, here at that point we are comparing the error, so we will get that value, some points are there. Then we are comparing that results with one high frequency value. Okay, means we are using triangular one, so you can see plus minus selection is there, triangular value we have selected. Now we are comparing like your gate driver circuit. Okay, comparing, it is called voltage mode of operation, voltage mode control. Okay, Comparing those values, finally we will get some PWM. That PWM directly you can feed it through opto isolator, then 555 timer, then one resistance to IRA 450. But here I am directly feed that value. Okay. But practically when you are going to design it in your laboratory, so you have to add one opto isolator, then add in any then add 555 timer as a stable multivibrator, then small resistance, then this one. So some oscilloscope are there for checking it. So here I am checking that values of triangular waveform and that control value, control voltage. That voltage is coming from that DI controller. So that is called control voltage. That control voltage should be comparable with your triangular, means repeating sequence. If it is not in the range, here you can see. So that triangular one is there, that is called sawtooth. Okay, sawtooth waveform is there, and pink color waveform is your control voltage waveform. Okay, so here we are comparing both. After comparing, we are getting some PWM, and that will be feed here. And here you can see the output voltage. The specifications are given. Input voltage is given, diode is given. Okay, MOSFET, which I have used, that also been there. So MOSFET, it should be in uppercase. Okay, so inductor is there, capacitor is there. Both the capacitor, one is controller capacitor, load resistance also be mentioned. Op amps, two op amps are there, one operational amplifier, function generator, current probe, and oscilloscope. So output voltage is coming nearer to the 5.4 volt, nearer to the 5 volt. Why 5 volt? Basically you are giving the reference value, that is the reference value, set value, control operation. So if you change that value 5 volt to 4 volt, again that output voltage is changed to 4 volt. Means if your controller is working fine, so it is try to, the system is try to provide you as per the value given in the reference. Okay. So here you can see the dynamic response of the buck converter. Same kinds of operation also been performed in case of boost converter. You know those values are given. Okay, one ohm as a ESR, 10 millihenry, so 10 volt is a source. Okay, again I am considering that boost converter output voltage set as a, but boost converter what happened? Output voltage will be more than your input voltage, but I am setting here 5 volts. So scaling down that value, the scale down here, you know that tracking value. I am considering this scaled value. Na? That scale value will be coming nearer to the 5 value. So that amount we have scaled down here. Okay, for designing of the controller. Okay, so if your boost converter having providing 100 volt, okay, you can scale it down up to 5 volt. Basically, why I am scaling down that voltage level? Basically, the bias voltage, the control circuit voltage should not be go beyond 15 volt. Okay, you have to scale down that voltage less than 15 volt. So you can scale it down up to 10 volt, 5 volt. So 5 volt is the standard. That's why I am scaling down that amount of voltage. Okay, that is coming here. Then PI controller is there. So then I am comparing those value, and finally again the PWM is there. So MOSFET is IRF P450 MOSFET we are using. Okay, mood diode is there. Then again we are comparing, and finally we will get that output voltage. Okay, so it's your output voltage. It is, you can see, more or less 5 volt. Okay, that 5 volt, and it's a current. Okay, current also coming. So these two experiment you have to perform by today. This is your experiment number. I think it is 8. Okay, this is your experiment number 8. Last class it was experiment number 7. But there are four DC-DC converters you need to simulate. Okay, and that link. Okay, so you have to submit the previous experiment means all those means experiment as early as possible. Please, I am suggesting you, please do not pending your work. Okay, so it's a voltage mode controller, boost converter with the PI controller. Okay, so I think all of you are able to understand. That file I'll share you. That file I will share you to your to the chat box. Okay, so you can you will get the reference from here and try to simulate it. Okay, So I think all of you able to understand. Do you have any kinds of have any kinds of doubt on it? Am I audible properly?
Yes, sir.
So I think all of you able to understand. Soumitra, are you able to understand?
Yes, sir.
Okay, I have already uploaded that file in the chat box. Okay, so please excuse me for 2 minutes. All of you, please go through that file I have given to you. Please download it and check it. Okay, hello students.
Yes, sir.
Yes, now Anandraj will show you some simulation on bridge converters. Okay, DC-DC bridge converters. Means what is DC-DC bridge converter? Last class I told you, means two simulations are there. One is your asymmetrical bridge, another one is your full bridge. Both are an example of a chopper. Okay, one is two quadrant chopper, another one is four quadrant chopper. Okay, so first he will show you that bridge asymmetrical bridge type of asymmetrical DC-DC bridge converter. Then after that he will show you that full bridge converter. Okay, Anandraj, am I audible?
Yes, sir, you're audible.
Okay, please share your computer screen and show your simulation step by step. Okay.
Okay. Is it visible, sir? Is it visible now?
Yes, it is visible. So tell them the process. How do you do one by one process? Then show your simulation. Okay.
Okay, sir. So we know that in a symmetrical bit converter we have two switching transistors. So we'll first select the transistors S1 and S2, and we'll be giving the gate pulses. The values are set to initial values will be 0 and the pulse value should be 6. The pulses will be 1 e raised to minus 5 and period should be 2 e raised to minus 5. So it's a 50% duty cycle, and we'll be using two more diodes. You must already know the library for that, and we'll be using a 20 ohm resistor and 4 or 4.5 millihenry inductor as the load, and both of the switches will be switched at the same time, so there is no need for delay in any of the pulses given, and the supply voltage is chosen as 100 volt. We'll be using two oscilloscopes, one to check the pulses of the one to check the gate pulses and other for the load voltage and current. And we'll be using a current probe which you can get from the instrument tab on the right side. And so you already know the operation of this one, you have already seen the manual. So I'll just show you the simulation on how the waveforms are coming. So in oscilloscope 1 we can see the square pulses coming. Since both of them are in phase, we cannot see the difference on them. And in the second oscilloscope you can see the voltage and current form. It's just as in the lab manual. Okay. So with proper values you will definitely get a waveform just like this one. So it will be two channel oscilloscope, one will be the voltage, another will be the current. What the current probe does is it will just convert the voltage like the current into a voltage value, so that it can be seen in the oscilloscope. So that will be the asymmetrical one, asymmetrical bridge converter, and your next circuit will be a full bridge converter. In this we can see we have 4 transistors and 4 diodes. So in mode 1 we have to conduct both S1 and S2 at the same time. Forgive the number, in the manual it will be S1 and S4 that will be conducting at the same time. And on the second cycle it will be S3 and S4 that will be conducting. So what's different from in the gate pulses is that we have to give a delay time in the gate pulse, because at the only two transistors should be conducting at the same time, and the voltage will be set as 100 volt as earlier. And while simulating this circuit, we can get a output waveform like this. It's similar to the one in your manual results. And the you can also see the current pulse. We can see the delay in the gate pulses that are also given to the transistor switches. So that will be output waveform. That should be we will get from this experiment. And you guys must already know the libraries from where you can get all the components necessary for this one also. I think the load resistance and inductor value is almost the same. We are using more diodes as bypass diodes. We will be using same 100 voltage source also here. The only thing you should take care of is the delays in the gate pulses that should be given, because only two transistors should be switching at a time. Sir, Arnab sir,
Yes,
is it okay, sir?
yes, it is okay. The magnitude difference is there due to scaling. Actually, you have made it here 100 volt per division, 1 me 50 millivolt. So pattern will be important. Magnitude, it can be calculated from the oscilloscope. Okay, so here you can see channel A, magnetic voltage is 100 volt per division. So here you can see almost peak to peak 2 volts are there. Okay, means peak to peak two channels. Okay, so one unit positive and one unit negative. Okay, so you have to calculate that average one. So 100 into T1 plus minus 100 into T off whole divided by T1 plus T off. At that way, students can calculate the duty ratio. Okay, so they can calculate the they can calculate the average voltage. So if you vary the duty ratio, so here you can see that value may be different. Means if you change the duty ratio, you can see that output voltage may be different, means positive to negative. Okay, normally this type of DC-DC converter means Beach types DC-DC converter, normally you are using 4 quadrant operations of the chopper. Okay, like you have one DC motor with you. Okay, and you have some DC voltage, and now try to control that motor into 4 modes of operation, means 4 quadrant operation. So what you need to do, that here you can see we are using RL load. Okay, some 20 ohm and 5 millihenry, that RL load we are using. Okay, so now if you change that duty cycle, okay, so it is, you can see all the simulation are in open loop. Okay, if you want to try to control the same simulation in the closed loop, what you need to do, you have to connect one voltage. Okay, that voltage is there across the load voltage, you have to select. Then again you can go to the voltage mode control, means that voltage, then you have differential amplifier like L084. Then you compare that voltage with one PI controller, maybe whatever controller you want to use, classical controllers. Then you have to compare with some triangular waveform. Okay, means repeating sequence. Two comparison is required. Okay, first you have to do it for triangular waveform, then we will get some PWM. That PWM will feed that first two diagonal MOSFET. Okay, or first two diagonal switch. That is the ideal diagram of the switch in multisim. Okay, then another that PWM also pass through some delay circuit. Delay circuit means there is some XOR circuit is there, so some delaying circuit, or it is also known as blanking circuit. Okay, that blanking circuit through triple five, then blanking circuit, then opto isolator means MCT2E. After that, any triple five timer, then you can fade it through the switches. If it is BJT, so directly you can fade it. If it is not, if it is MOSFET, so you have to fade it through the resistance. So by that way, closed loop it also been working. If it is in RLE load, means motor load, then what happen? In case of motor, you have to control the speed of the motor. motor. Okay, means your output, what is the output of the motor? Input is electrical energy that is coming from here. That if you vary the duty ratios of those switches, so automatically that output voltage will be vary. So you say like that, armature voltage control. Okay, so armature voltage may be controlled by the controlling of the duty ratio. Then what will be the output change? So motor input is electrical energy, output is mechanical energy, means shaft. Okay, so you can sensing the shaft positions, okay, by the position sensor, or you say like that, that is RPM, means tacho generator you can use. So what is the tacho generator? Is an example of a transducer. So input is your RPM, output is your electrical energy. Okay, that electrical energy is your compared. Okay, that electrical energy is value is very small, so you have to amplify that energy. Okay, today I have discussed that in my manual, so I have given as a reference as a 5 volt. So that tacho generator voltage will be amplified through a amplifier. Okay, and it should be, it may be 5 volt. Okay, then compare, again one differential amplifier will be there, differential amplifier with PI controller, that today I have discussed in my manual. Okay, so then it will be compared with the reference voltage, then PI controller output will get some control voltage, then control voltage will be compared with some repeating sequence. After comparing the repeating sequence means LM311, today I have used for define for comparison LM311. Okay, so comparator. Okay, so after LM311 you will get some PWM. So that PWM, one portion of that PWM will be fed through opto isolator, then NE555 timer and diagonal component of these two switches. Okay, and another portion of that PWM pass through the blanking circuit. Okay, then opto isolator for the optical isolations, then NE555 timer, then one resistance, then another two diagonal MOSFETs. Okay, by this way we can also operate in closed loop control of a closed loop speed control methodology of a DC series motor by DC motor by using that full bridge configuration, DC-DC full bridge configuration. So whatever you are want to do by varying of the duty ratio, it may be working in the quadrant 1, then quadrant 2, quadrant 3 as well as quadrant 4. I think all of you are able to understand my idea, means all of you are able to understand my that concept I am sharing with you. Is there any doubts from the students end? All of you able to understand the concept? Vishwas Kashyap, are you able to understand my point?
Yes, sir.
Okay, then Hambir, Jagannath, all of you are able to understand my point? Yes or no?
Yes, sir.
Aditya? Okay. Sufyan, are you able to
Yes, sir.
understand my point? Okay, so I think all of you getting my point. So next class, what you need to do, that I have shared my idea, means shared my manual. Okay, I have already uploaded that manual also in your chat box. Please download it and go through it and try to simulate it and complete and submit up to experiment 6. Sorry, up to experiment 7. Today I have given the manual for experiment number 8. Okay, so my suggestion is that to your CR, means Soumitra, please submit all those value up to experiment number, sorry, all those write up. Okay, up to experiment number 7, those pending write up everything as early as possible. Okay, basically that if I have completed up to experiment number 8, today I have discussed on experiment number 8. So means control closed loop operations of boost converter and buck converter. Okay, so to next week you should submit that report. Then we will discuss about experiment number 9 and 10. Another 2 weeks we will complete. Okay, so that's why my suggestion is that as early as possible all of you submit that pending report. Okay, then we can fix up the date of examination. Okay, I think all of you will to understand. Thank you. So then one exam will be conducted like your every class. Okay, so please be online, and I request that Anand